Okay, so today we're going to be doing the gas law lab, and we have 4 lab stations for the gas law lab. And the first lab station is going to involve a balloon. So here we have a balloon, and it doesn't look like a very inflated balloon, and that's done on purpose. So as you can see, this balloon is not as inflated as we would like it to be, and this is done on purpose. So what I did with this balloon, if I can catch it, is I purposely let out some of the helium gas in this balloon, and you can see there's the tape on the balloon, and that's where I poked a hole in it and I let some of the gas out. Now I did that so that the balloon would kind of float halfway, or kind of on the ground, or kind of halfway between the middle of the room and the ground. So you can see that it's floating that way. Now, the whole purpose of this lab is to get you thinking about pressure, volume, and temperature. Now this is what we did the can crush lab on, but pressure, volume, and temperature are incredibly important for gas laws. So this balloon happens to have a volume of gas inside of it. It happens to be a volume of helium gas. Now I want you to start thinking about like a balloon, like a hot air balloon. Now what happens when you heat up the air inside of a hot air balloon? It rises. So when gas happens to expand, it rises. It becomes less dense and it rises. And when it becomes more dense, it sinks. And so that's what's actually happening with this balloon. So as the volume of this balloon expands, it rises. As the volume of it condenses, it goes down. So what we're going to do is we're going to use a hairdryer and we're going to heat up this balloon, and you're going to see it rise up into the air. So I'm going to go ahead and set up the camera on a tripod just so we can see that. And you can see just by adding that small amount of heat, our balloon instantly rises. So what happened there? What changed? Well, what happened is the gas expanded, and the gas became less dense and it rose. Now we have to think of this in terms of temperature and volume. So as the temperature went up, what happened to the volume? So as the temperature went up, volume changed. So we could say that volume and temperature have a very specific relationship, and we could write down that relationship on the board. And we could say that volume and temperature have an inverse relationship. As one goes up, the other one goes down. They have an inverse relationship. Question 2 deals with pressure and volume. So in question number 2, we end up having a syringe, and I have the syringe right here. So here's the syringe. And this syringe happens to be measured in teaspoons, and milliliters. And we're going to use milliliters. And now what I've done with this syringe is I've used a match and I've sealed off the end so that air cannot escape. So this has been sealed. And then I've pulled this back all the way so that this is at the 10 milliliter mark. So that's at the 10 milliliter mark. So the volume that's inside of this syringe is 10 milliliters. Now what's going to happen is we're going to put this syringe into this Coke bottle, and we're going to use a device called a fizz keeper. Now you may have heard of a fizz keeper before. A fizz keeper is something that people have tried to use to keep pops and sodas from going bad. And what they do is they just screw onto the top of a Coke bottle, and then you pump them up and they add pressure. They don't really work very well, but they're going to be very useful today for what we want to do. So what we're going to see is we're going to see the effect of pressure on volume. So when we add pressure, we're going to see what does the pressure do to the syringe. Does the pressure push the syringe in? And if the pressure pushes the syringe in, what effect does it have on the volume of the syringe? What does pressure have? What effect does the pressure have on the volume of the syringe? Again, we have a 10 milliliter volume in there. Will that pressure in the bottle crush that syringe so that we have less than the 10 milliliter volume? So let's find out. So I'm going to go ahead and start adding pressure. And you can look inside of here and you can see it's still at 10 milliliters. And now we can look at the syringe, and we can see that the syringe is no longer at 10 milliliters. The syringe is somewhere at the 7 milliliter mark. So it appears by adding pressure to the container, when pressure goes up in the outer container, the volume that's being affected causes pressure to go down. So the volume is affected. So as pressure goes up, volume is affected. So this is a 1-to-1 ratio. So we could write that relationship on the board. We could write that relationship as P as when pressure goes up, volume goes down. And we could do some very fancy math. We could do some very fancy math to make this work out. But basically, when you do the math on this, we always get that pressure and volume are directly proportional. So pressure and volume are directly proportional. So these are the two formulas that we have described so far. So this one's called Boyle's law, And this is the other formula that we described. So volume and temperature are indirectly proportional, and pressure and volume are directly proportional. So we've discovered both of those using this lab. Lab Station 3 deals with pressure and temperature. And so we have a very similar setup that we did in Lab Station 2. Again, we have a bottle, and it again has a fizz keeper at the top where you can add pressure. And we have what's called a liquid crystal thermometer, and so this is something that would be used in a fish tank. And I don't know if you can see it very well on the camera, but in a liquid crystal thermometer you can normally see a highlighted liquid crystal display that displays what the temperature is. And so for me, it looks like 26 or 27 degrees Celsius, about 78 or 80 degrees Fahrenheit. That's about how hot it is inside of this room right now. So what we're going to do is we're going to pressurize this container, and we're going to see the change in temperature. Does temperature go up or does temperature go down under a high pressure? So that's what we're going to do. So right now at atmospheric pressure, it's about 26 degrees Celsius. That's where we're starting at, 26, 27. And it really helps to use a clear bottle, something without any condensation, and I've done my very best to make sure that this bottle is completely clear. Sometimes if you have water vapor or anything in it, it's very hard to see. And I really hope you can see this with the camera. But again, it's about 26 or 27. And so what I'm going to do is I'm going to pump this up really well, and we're going to pressurize it. And so we're going to see the relationship between pressure and temperature. If we increase the pressure, does that increase the temperature? Or does that lower the temperature? We're going to find out. Okay, I think that's good. We've pressurized it, and I don't know if you're going to be able to see it very well, but I'll do this at an angle. You can see the temperature is now at 32, 34, and I'm going to do this at a few angles, so hopefully you can see it. So the temperature has gone up as the pressure has gone up. It turns out that these two are inversely related. Pressure and temperature. As one goes up, the other one goes down. That's just how these are related. So pressure and temperature are inversely related. So yeah, that's basically the relationship. Let's see if we can see it if I take this out real quick. And yeah, you can see where the 32 is, and it's probably going to rapidly drop really quickly. Yes, but that's the example. That's a real clear demonstration of pressure and temperature. So we can write our new formula on the board. We can write that pressure and temperature is equal to pressure and temperature. So that's our new formula that we have. So we've discovered three gas laws so far by doing our lab. First, that V over T is equal to V over T. Second, that PV is equal to PV. And third, that P over T is equal to P over T. We have one more station inside of our gas law lab, and it's really more of a confirmational step from these three formulas that we have discovered. So it's going to be more of a confirmational formula of PV equals PV. So basically, you have two items that are inside of this bottle. We have ketchup packets, and inside of these ketchup packets, there are air bubbles that are at the top. And we also have an eyedropper. And this eyedropper that's in there has a bubble that's inside of it. And what we're going to do is we're going to apply pressure to this bottle. And if we apply pressure, what's going to happen to the volume? Now, again, if the volume, like remember with the balloon, if the volume goes down, the buoyancy goes down, and then these should sink. So we should see these sink if we apply enough pressure. Now that's going to confirm our relationship PV equals PV. So let's see if that happens. So it looks like the eyedropper is going to go first, and the ketchup packets are on their way. I'm going to put the marker down. So it looks like the eyedroppers made it down there, and the ketchup packets are just starting to go. Okay, so everything's been pumped down, and as you can see, the ketchup packets are still somewhat buoyant, but they are below the water. They are below the water, as is everything else. So pressure, and what I'll do is I'll release the pressure, and you can see them bounce back up. Quite a bit of pressure under that, and you can see them bounce right back up. So anyway, with these three formulas, what we can do is we can derive one single formula. So these are three separate gas laws that we can derive a single formula from. Now, it turns out that these can all be merged into one single formula, and let's go ahead and do that. So these can all be merged into PV over T is equal to PV over T. So that's all three of these. That's all three of these merged into one single formula. So this one formula is called the combined gas law, and it deals with pressure, volume, and temperature. So this is how pressure, volume, and temperature are all related. And this is what today's lab was all about. Thank you.